Jun, are you around? Are you ready? I see your shared screen, but I don't hear you. Still no sound. Can you hear us? I don't hear. Do you all hear him?
No.
No. Oh, okay. Give 1 minute. Okay, let's wait. Yeah, okay. See if you can fix it. Let us know if you need more time and we can move to the next person first. Thanks, Jun for hosting just now. Yes, great.
That's okay.
Like a lot of things happening at the same time.
Okay.
Can anyone hear me?
Yes, great. Welcome.
Thanks.
ready?
There's something problem with my mic. Sorry about that.
No problem. Okay, when you're ready, please start.
Okay. So, hello everyone. My name is Jun. I am from the Institute of Brain and Mind Science in National Taiwan University. My topic is predict individual emotional changes in competitive tasks by using RS-fMRI connectivity data. And first, I want to talk about some background. According to previous study, in a competitive relationship, an individual's emotions are easily affected by the differences in status between the two parties. For example, here is a competition with two independent outcomes. One is the result of the competition. I use a Chrome for tell that people is win or lose. If there is a Chrome, that means that people will be a winner and the other will be a loser. And the other outcome is a random punishment assigned to the participant. For example, if you see this icon, it means this person get a punishment with lose his money, and the other one won't get a punishment outcome. And if in this competition, if I become, for example, if I become the winner, but witness my competitor being punished, I may feel comparison toward themselves and toward them. And conversely, if my competitor may be jealous of me. However, if I achieve vicarious but also have to face the punishment, I may develop a sense of unfairness while competitor glad about my situation. And previous study have, and the other big one is previous study have demonstrates that specific patterns of resting state connectivity can predict individual differences in emotional traits and tendencies. For example, in this study, the ball signal is negative correlated to the resting state fMRI ball signal is negative correlated to the subjective happiness score. But most research only predict emotional changes in a single situation. Therefore, I'm curious whether an individual's resting state can predict emotional changes in different of situations, multiple different situations. So in sum, I attempt to use the individual's resting state to predict the individual's continuous emotional changes across multiple situations, like the picture which we see here. And my data set is from 30 participants provided by my senior Mimi Lin. In this data, we will see the emotional responses of the subject after facing the following 12 combination of outcomes. And it should be noted that these three types of outcomes, that is win or lose, self or other receive punishment, and three types of intensity punishment are independent. So there's 12 kinds of outcomes. And next is about my method. In the first part, I'm going to use a CCAP for resting state MRI preprocessing and functional connectivity. And why I use a CCAP for preprocessing is because the resting state MRI is more susceptible to unrelated signal than text-based MRI. So some specific signal processing, for example, filtering and trend removal may necessary to reduce the signal. And surprisingly, CCAP also performs a functional connectivity analysis while processing the data. Therefore, I will use the result from the CCAP functional connectivity as a feature for machine learning. And I will discuss CCAP in more detail later. Now, let's talk about the part of machine learning first. Here, I will focus on the modeling part. Since my sample size is only 30, that means it's really small, but having a large number of outcomes. So I will choose to use a simple model such as SVM or random forest to try to optimize it. And now I'm going to introduce CCAP and show my current progress at the same time. CCAP is a program specifically designed for resting state fMRI analysis and can be executed over the internet or locally. In addition to preprocessing RSMRI BIDS file, it will also perform some analysis on its own, such as VNHC, which provide information about the symmetry of functional connectivity between brain regions, or ReHo, which provide information about the regional synchronization of neural activity. And network centrality measure the importance of influence of a particular voxel or node within a brain network. In other words, it assists the degree to which a voxel is connected to other voxel in the network. And ALFF represents the amplitude or intensity of low frequency fluctuation in the fMRI signal. And the last but the most important part about my project is SAC, involving selecting specific seed regions or region of interest, and calculating the correlation between the time series of the seed ROI and the time series of all other voxels in the brain. It provides a measure of functional connectivity between the seed region and the rest of the brain. And here is the programs I try to execute default CCAP on batch as one subject. And it has we are that it had made a mistake when I'm processing, and so I'm still trying to fix the problem now. I may try to check the data structure for its report on the crash file, or remove the main test session, because CCAP is specific for the resting state MRI, so it may is because I use the name test in the file, so it make the crash appear the crash situation, or I will use to change the parameter setting for CCAP to make sure that the crash report won't output again. And here is my project.
Oh, okay, all done. All right.
Yes.
I was wondering if you, thank you so much for the presentation, very cool. So I was wondering if with the error that you got, right?
Yes.
Did you try the data with, let's say, a standard FSL pre-processing and then you got an error also?
Can you please repeat again?
Did you try with the data with maybe, because you've got this error using the CPAC kind of the package, right?
Yes.
So I'm wondering if you tried it with maybe directly, if you just use FSL to do the, what is this? To do the, is this just to do some adjustment of the face image?
In this part, it's just for preprocessing for the for all states MRI image, and
yeah,
it only outputs some really basement some
oh, did you drop off?
Can everyone hear me?
Yeah, I can hear you now.
Oh, sorry about that. This part here we can only see it just only outputs some parameter for pre-processing. So I don't know what's the problem about this, why it just cut it here.
Because one way would be, I was wondering if it is the data or the way you are using CPAC, that's the issue, that's the thing. And if you've tried the data using other method and it's worked, then that tells us the data is okay. But then I'm not sure if that's the case here, right? Yeah.
Does you mean if I use, for example, SPM for preprocessing
maybe
and
some other
work?
method. Yeah,
I have tried it, but in SPM it's actually work, but I don't know why in CPAC there's something wrong with it. I think it may because of the BIDS structure, maybe some different in CPAC or something like that. I'm not sure about that.
Yeah, then you have to kind of figure out what CPAC is expecting in terms of format and parameter entry values, right? So whereas SPM has some presets and stuff. So okay. Any other questions? All right, if not, thank you so much. We will move on to the next person, who is Min Rou.
Hello.
Hi.
I think I'm Zhijia. Think maybe not.
Can't hear you. You're breaking up. Don't see.
Mingo something to.
What?
Wait. Let me type.
Oh, okay. Then let's move on to the next person. Two people together, Yan-Zhen and Tsu-Yueh. Okay, I see the screen. And
can you see my screen?
yes, and your slide also. I see that.
Okay, so we're Yan-Zhen and Tsu-Yueh, and so because we actually come from a background with very little knowledge on EEG data analysis, or Python, everything.
Okay.
We just want to focus on the EEG processing and get into familiarize with the data. So we're using an open data set from OpenNeural, and it's EEG data from an auditory oddball task, and we'll provide the link in our GitHub, and here's also. And so for each participant, so there's actually 13 subjects, and for each subject, they do 3 runs of the same session. And so in total, there are 750 stimuli, and 70% are standard and 15% are oddball. And when they heard an oddball, they have to respond it by pressing the key. So we're going to just run through the whole process of our pre-processing using subject 1 and run 1. And first of all, we read the raw data, but we are going to use the M&E Python. So we read the SET file, and then we look at our raw plot. And so this data set is actually pretty good because the events ID is already on there. So that's pretty good, and we don't have to like find the events and then plot it on the plot.
Okay. And then after we read the raw data, we select a subset of the channels. And by examining what channels we have, initially we found that there are 79 channels, but only 65 of these are the EEG channels. So we eliminated the other channels
I don't know why.
that
I'm
are not the
sorry.
EEG channels.
Yeah.
Yeah, so then we use the pick types function to select only the EEG channels. So we are left with only 65 of them.
Yeah.
Yeah, and this is a list of our selected channels. And then we plot them to see where they are located. And this is them with the location presented.
And since we don't have the M1 and M2 channels, so we're going to use like the closest 2 channels to re-reference in our data. So for re-referencing, we choose T7 and T8 as our reference electrodes. So we re-reference it by averaging the T7 and T8. And so and we examine the re-referenced results. And after we do filtering, so we plot the power spectrum before filtering, so it's kind of look like that. And after filtering, where's the, so we're using a bandpass filter of from a 0.16 to 30 hertz. We choose this range due to reading some other papers that do oddball task as well. So because we see that most people use this range, so we're going to follow this range as well. And so after filtering, we compare like the before and after. So it kind of look like this. So we can see like after here, we filter out the higher frequency. And so we zoom in and it kind of look like that.
And then we extract the event. As previously mentioned, that this data set already has pretty clear annotations of their events. So we get the events from the annotations. And then we found that they have these events where, and mainly we'll be looking at their responses in the standard and when they successfully responded to the oddball. So these are the 2 events that we will be looking at.
So after that, we create epochs for the events, and we reject the noisy epochs with this criteria. So if the peak to peak amplitude is over 100 microvolts, then we reject it. So this reject criteria is included in the epochs object here. So, and then here's our time window, and we look at the data again, so we can see like the dotted lines here is the epoch plot. And we also examined the apex object of this one is for the standard condition, and this one is for the oddball with response. That means that they hear the oddball and then they correctly like press the key.
And then we will create evoked data using the epoch average, and we do this for each condition, which is the standard and oddball with response. And these are the plots of the evoked objects. And as we can see in the lower plot, where around 200 milliseconds, there's a positive going wave, and which this could be a P3 reaction that people would exhibit when they are when they hear an oddball.
And we also do the plot join. So for this function in M&E, so they join the butterfly plot that we just plotted, and then plot the local peaks with the topo. But we don't know why, but like for most of our data, towards the end, there's like really high noisy, yeah, high amplitude. So when they plot the topo is all like towards the end, and we don't know how to resolve this this problem. And we also plot like for each channels to compare the standard and oddball conditions. And at the end, so before is just subject 1 and run 1, and then we wrap it all up in a pre-processing function. So this is our function, and so then after defining the function, we can loop over all 13 subjects, and for all 3 runs, and then we actually combine, like for subject 1, we combine the run 1, run 2, and run 3. And so eventually, if we want to, let's say, look at the subject 8, and we can just like change this, and then we get like the compared plots like we can see before. So we can also see like the peak here that we can see in subject 1 as well. But then when we try to look at all of the subjects, and some of the participants' plots are not looking really well, and so far, me and Zira don't have enough knowledge on EEG to know how to interpret this, and we don't know whether it's the problem with our pre-processing processes or the data, or if there's other effects. So we're hoping to get some feedback or suggestions from other people as well. So here's the end of our presentation, and thank you so much for listening.
Thank you.
Okay, very good. It's very bold, and obviously, yeah, it's new work for people, for some of you, but then that's part of the experience. So very glad that you are trying. I'm not EEG expert. I think some EEG people might see something I don't. I think this looks actually pretty normal to me.
Oh,
Really? I don't know.
unfortunate.
Any EEG people want to chime in? Yeah.
Sorry, I can't make meaningful comments right now, but I will definitely check the recordings later. And I know you guys have been putting a lot of time into this, and I think you've done a great job. So I'll definitely check the recordings. Yeah.
And Prof. Shi also put some of some link that you can check for the tutorials. Yeah. I think a word of advice here also is that you know, the data that if you want to try so many subjects, I think part of it also is to focus on one subject first. And then when you get yourself clear, then you can move on to more.
Mm-hmm.
Yeah.
Hey,
Yeah,
thank you.
I think so far I think individual subject always sometimes looks good, but sometimes it looks horrible because that's how individual data looks like. Yeah. So for me, sometimes I download the example data and I always start with one of them, and usually that looks pretty good because I get a lot of trials. But then when I proceed to process more and more subjects, then well, you start to see some data looks really horrible. And usually, conventionally, while running experiments, we will have an idea that one third of the data might need to be dropped out from the process.
Yeah.
Yeah. So it's fine if you found something don't look make any sense because that's how a single subject data looks like. Yeah.
Thank you.
Thank you.
And also, I think you chose a good task because the oddball effect is really a strong one, right? So, you know roughly you are in safe ground, what you expect to see, that the oddball should be a very strong response compared to the very frequent events and all that. Okay. So yeah, keep plugging at it, and you will, we learn from trial and error, and we learn from trying, and then we get better and better at it. So this is good. Thank you so much.
Thank you.
Okay, we go to the next person who is Li-Xuan. Alex, right? You here?
Hello, and sorry.
I hear you.
Okay.
Can you turn on your video?
Okay.
Okay, great. Yeah.
Yes, I will share my screen.
Yes, please.
Okay. Okay, can anybody see my screen right now?
Yep. Looks good here.
Okay, thanks. So, okay, I will start it.
Yeah, share the slideshow. Okay.
Okay. Okay. So, my project, due to some reasons that inadequate open data, so I decided to change my topic from the detecting eddy cause atrophy to this one, brain tumor segmentation. But the underlying method is the same with the original idea. Okay, and so I changed some key concepts here. That is, I want to segment brain tumor area on brain structural MRI images using foundation models fine-tuning. And then my data sets changed to using some public data on Cargo and the famous BRA-TS from this challenge. And I use the data set here for fine-tuning the model and then evaluate on the brackets, which is more complete data set. I want to, through this kind of evaluation, I want to see if this fine-tuning method could be could provide some generality on the foundation models. So and the conundrums I have just addressed about the computational resources, which I want to appreciate to NCO CSI department. And here are some resources I want to show to you. Okay, and the first is fine-tuning resource in terms of dice and cross entropy loss. And for fine-tuning, you can see here is slow degradations of a loss, which is a stable training, which looks really great. And I also do some qualitative resource that compares the original foundation model and the fine-tuning model. The leftmost is the ground truth, and the middle one is from only foundation models without any training on the brain tumor segmentation dataset. As you can see here, with this bounding box, it doesn't get any meaningful area of the brain tumor. But with the fine-tuning model of medical SAM, it shows great results of brain tumor segmentation mask. And with the dice score from 0 to 0.8, but this is a relatively extreme cases. But here's another one. This one, although it looks pretty great on fine-tuned model, but it sometimes occurs when SAM foundation model itself is better than med SAM. So this is a productivity resource that randomly selects a case and fit into a model and get the results. So what if we evaluate this data on the entire data set? So I have to do some basic statistics of the model performance. And here's a quantitative resource comparing original foundation models and fine-tuned models in terms of dice score. And this statistic is run on the BRATIS 2021 challenge dataset, and it contains 1,666 scans, and I do random sizes of each scan with the T2 weighted MRI images, and then feed into both the foundation models itself and the fine-tuned model. And the left one is foundation model itself. Its average is about 0.6, and we can see the fine-tuned model is perform better than the original one. But it also have space to improve because the overall average the dice score is only about 0.7. And I could quick walk through to my Jupyter Lab notebook for you guys. And yeah. So here let's load the BRATIS 2021, the second scan with T2 images, and the ground truth is this one, and we execute it. And this is a visualizations of the scan. So I can choose which slides I have interest in. And then, okay, if I want to do this, okay, I will select the slides as 94. And then just execute the result. And it will print out the original MRI sizes and corresponding ground truth, that is brain tumor mass. And then we'll do some inference on the model. Okay, here. So we got the ground truth and the foundation model results and the fine-tuned model result. As you can see here, the fine-tuned model is performed better than SAM itself. So it's close to. Oh yeah, ground truth is determined by the pathologist, and it's verified by the medical team on the original challenge published. So the model shows a pretty good generality on this task, and this model is because my training data is relatively small. So the model performs like a little bit beyond my expectations. That is, it could learn really efficient. Yeah, and that is a quick walkthrough of the demo. And for the fine tuning, I will not go through the details, but I will upload this notebook on the GitHub for your reference. And okay, so and this is my project, and I want to special thanks to NCU CSIE department providing powerful computational resource to make this project practical. Thank you.
Okay, great, Alex. I have one question. Yeah, so ground truth is always human rater. So in this
Yeah.
case, then the way the model is applied, is it learning the human criteria and not really about some tissue property? I wonder. You know what I mean?
Pardon? Sorry. Please. Learning human criteria on real tissue property. I think that the model. Sorry, but I'm not the medical background, but
Yeah.
I think that this model is generalized to like to mimic the human behavior of selecting the area of the tissue. So I think that he uses the MRI images and just through the computer vision algorithms. So I think that the explainability of this foundation model is not that explicit. So that is some conundrums of recent deep learning models.
Okay.
Yeah. So the explainability is it is a question, and and it's behavior like black box. So so I don't know the exact reasons how it could perform so much better. But I think that it is due to the quality of the data for original foundation model. Yeah.
Okay. Yeah, I mean, there are a lot of ideas about this, and I would suggest to you that the way this is being done is if your ground truth is about human, like the radiologist draw like this and say this voxel is pathology, this voxel is normal, and the AI is just learning that. Then what the AI is doing is trying to match the pathologist's eyes, not necessarily that there is some real tissue difference in the image, right? Which is fine. I mean, that's one, obviously that's one very important way to do it. And I think one challenge, not that for your project, this project is fine, it's great already. But for me, maybe future would be like if we could somehow figure a strategy to train AI to not rely on human rater kind of as a gold standard. Because if you say that 0.9 accuracy, what that means is 0.9 accuracy to match the human rater. But if human rater is lousy, then the 0.9 accuracy is also lousy, right?
Yeah.
So if there is a way we can use the data from the AI perspective to do some maybe, I don't know, data-driven clustering that doesn't depend on human rating, then maybe that can be some future idea. But this on its own is fine for this project.
Yeah. So you mean that it could be learned from the unsupervised manner, right? Like we don't
just
have
from the image itself. If I give you a bunch of like pictures, and the AI learns to itself unsupervised to distinguish, like, hey, these pictures are different from these pictures, right? No human intervention here.
Yeah.
And we can see what the AI is seeing. You know, maybe.
Wow, that is
that's
that's
definitely
inspiring.
That's definitely much more difficult than using it to match some human decision as the outcome, right? So I think still a ways to go, but obviously this just for you to think about.
Okay, thank you.
Thank you so much.
I will
okay.
try.
Thank you. So we have the last person. Is that the last person? Rong-Xuan. I see it's the last person on the list. Rong-Xuan.
I think I'm the last person.
I think so. Yeah. Great. So please share your screen.
Can you see my screen?
I see your screen with the browser.
Yep. Yeah. And the topic of my project is breath and deep EEG detection.
So the M2 this project is aimed to classify the different motion phase through EEG signals. And there are 6 motion phases in this experiment, including hand start and touch the object, then grasp and lift the object, and finally replace it to the table and release the object. The data set is from Cargo, and there is 12 subjects in total and 10 series of trials for each subject, and approximately 30 trials within each series. So my goal for this project when the project page is to achieve at least 80% accuracy, and learn how to implement different methods for the EEG signal detection. So I think we can see the results first. I use PCA and random forest to classify the data and get 99% accuracy for the training data and 80% to 93% for the test data. But I think there must be something wrong because I think I didn't pre-process the EEG signals well. So it shouldn't be such high accuracy, I think. But the test data includes different subjects and series, so I think it is not a problem about overfitting. But no, I still have no ideas how to fix this problem. So
sorry, can I check again? Can you tell me a bit more about what the grasp data and all that, and what do you mean train and test? Why are you training and why are you testing?
train data and
Or
test
you
data.
mean you are training and testing the model to separate grasp and the other kind of action? Is that right?
The data include labeled events, so I can use the data to train the model.
To train the model to do what? Sorry, that's the question.
To classification, the motion phase.
So yeah, to classify whether this is a grasp or or the other action.
Yes, this 6 motion phase.
Okay. So it has to classify 6 different things.
Random forest is the model it can like unsupervised to classification.
Yeah, but the classification is to classify into 6 different things, or
yeah.
Or each one to classify one versus the others. You know what I mean? Like there's 6 different categories here. You are telling the model to classify a given data to 6 different categories. Is that right?
Yes.
Okay. Thank you. Not just to clarify. Okay.
Okay, so I move on.
Yeah.
Okay, so I think the result is with some problems. So I want to focus on what I learned and practiced during the BrainHack School and through this project. So first of all, is PCA and ICA. Before this project, I just know PCA and ICA is a common use in signal decomposition, and I have seen some example, but never implement by myself. Now I know how they work in the mathematical method and know how to implement them by Python. But I use the scikit-learn library to implement this method. But there are some problems because I cannot determine which components should be discarded after ICA. So I stuck at this phase. And I also learned M&E Python. I have witnessed teacher Xu demonstrating the usage of M&E Python in the class. And now I know how to manipulate with the BID data and try to use CSV file to create the info by myself. So this is how I work with it. And I also use M&E Python to do to do ICA, and this is the result. And I have referenced the tutorials on the EEG lab, but I still feel confused about how to choose the component, so like eye movement or other noise.
Okay.
And I have also used the wavelet transform with Python, so that I want to apply it to a CNN model. But now I encounter some unresolved data structure issue. So, okay. So I think after the BrainHack School, I still need to learn how to properly pre-process the EEG signals so that I can apply different feature extraction methods and achieve the desired result. So I will continue learning and completing this project after this course ends. And this is my presentation. Thank you for your listening.
Thank you. I wonder if you can tell us more about, like you said, the result is 80% or 90%, and you said this must be a problem. Can you tell us more what you think the problem is?
Yeah, because I think I didn't pre-process the EEG signals, so I think it got this high accuracy is weird. And I also see the results is get all zero. Just
What do you mean the result
so
is zero? Sorry, what do you mean the result is all zero?
the SDE event file. The motion phase is labeled with 1 and 0, means if it is in the phase.
Oh.
Okay.
Okay.
And in the data field, there are almost all zeros. So if the result get all zeros, it can achieve the high accuracy, but it's not the truth.
Okay.
Okay. Any other questions?
So what I just wonder, so given that there are 6 motion phase, so how does that labeled in the data? So is that means that they have one segment of data, it's labeled as hand starts, and the other segment of data is labeled replace, or it's a continuous data with some impost label on that?
I can show you the labeled data. It is the 6 motion phase, and we can see most of the data got all zeros. So this is why if my result is all zeros, then it can get a higher accuracy. And there the label here.
Okay, here's one label. So so the data,
the label is,
each row represent 1 time point. Is that correct?
Yes.
Okay. Well, okay. And so I think with the I think it's while running the model, it's always good to be skeptical about yourself, because sometimes when got for me, I will also doubt myself when I first got a very high accuracy. And regarding pre-processing, I think MLE Python has some examples. So once you finish ICA modeling, then the following are just some recurrent steps. So you can just select one component. For example, in your previous figure, this component number 1 looks like a vertical horizontal vertical eye movement. So you can just plot the result after removing that component. So it will just give you a plot to compare before and after removing that component. And if that looks good after removing that component, then you can accept that one is the component to be removed. And then if that component, after removing that component, doesn't make any change in the data, or even worse, you see some unusual artifact after removing the data, then that means this is something should not be removed. Then you usually you can just remove like either one or two the component related to eye blink or ECG component, then that should be enough to give you clean data. And also you mentioned about some pre-processing steps, so maybe you can try to do some bandpass filtering, things that you can already put the data into MAE Python, into the container of MAE Python variables. So then after the pre-processing step, you can just use the get data method to export the data onto the conventional NumPy ND array. Then you can go on with your original pipeline to build a model. Yeah, but I think you already figure out how to transfer data from the original format and to MA Python. Then I just need some time to be familiar with the pre-processing steps. Yeah. Okay.
Okay, thank you.
Okay. Any other? I agree. I think actually a lot of this, maybe when you say this, you say it's weird or what. Try to plot it out and visualize, so we can see why it's doing or what it's doing. It'd be easier to make some conclusions there.
Oh, yeah, I got it.
Okay. Then nothing else? If not, then that's it. That's the last presentation. Yay! And let me stop recording then. Hang on a minute. Yeah.